So, matrix transformations is what we're going to be dealing with today. And we're going to really be dealing with matrices as transformations and then the resultant matrix from a transformation. These transformations really, what this is underlying is transformations of your graphing space, which is used very often in, you'll do some more with this, not in calculus, but you'll do some more in higher level, and if you take multivariable and differential equations, oftentimes the math that we want to do is, and the shapes that we get are difficult to do calculus on in our regular space, but if we transform them to a different space, right, it makes some of the math a little bit easier. So I know that sounds kind of weird, but just to tell you that where this kind of math that you're doing leads to. And then honestly, the most applicable field that this kind of math is used in is computer programming, but computer programming specifically for game animations, right? And 3D graphic design and stuff like that. It's kind of cool. All right, so first, matrix transformations, a definition. So we're going to talk about linear transformations. And a linear transformation is a matrix, and it performs a transformation on given position vectors. So that's kind of like what the warm-up was about. Such that the origin remains fixed. So truly, in each one of those warm-ups, right, I really had another position vector. In 2D space I had 0, 0, and in 3D space I had 0, 0, 0. And all the transformations that we're going to do are going to leave the origin where it is, and all lines remain lines. Now that seems kind of weird, right? What do you mean all lines remain lines? So let me show you a quick animation of these things. So here's an animation of linear transformations in space. Whoa! Did you see that nonsense? Let's do that again. So there's my 2 unit vectors, and watch them translate. Whoa! Do you see where the red and green vector went? Like, kind of crazy. Let's look at this next one. What do I mean by all lines remaining lines? That transformation that I just showed you, notice the origin stayed where it was, and that the vectors 0, 1, and 1, 0 stayed in the transformation. When you saw the transformation of space, everything still was, right, the grid was still a grid of lines. So I'll show you an example of a non-linear transformation. Whoa! Check that out. And maybe you can kind of sort of see now where maybe this might be useful in designing an online game, right? That's a non-linear transformation. We deal with some of those in, right, there's a linear transformation. That was linear, and the other was non-linear. Kind of crazy, right? There's a better drawing of a cube. I'll use that later. Another way to think of linear transformations is the transformation matrix. Think of it as a function, right? So you're like, there's a function, a transformation function, and the input is a matrix of position vectors. Doesn't really have, right? It's easier to think of position vectors. And then when I perform the function, the output is another matrix, but that it's been transformed. And I can kind of sort of think of that as, where did my unit vectors go? So here is a picture of what we did before, right? Before transferred. So here is, if you want to think of it, the position vector 0, 0. Here's the position vector 1, 0. Here's the position vector 0, 1, and here's the position vector 1, 1, right? So all of those position vectors Whoops, I missed. Did you get the idea? Right, and if I connect the tips, I get this square, and I want to take that original unit square with those unit vectors, and I want to perform a transformation on it. So here's what I'm going to call my transformation matrix, and maybe you recognize it, right? These are the x's, this is the y column. So here's my transformation matrix, right? X column, y column. X kind of, right? So I want to do this transformation matrix onto the unit square matrix. Now notice what I've done with the units, 3 separate matrices, 3 separate columns. I just put them in one matrix, right? 1, 0, 0, 1, and 1, 1. So notice my transformation matrix is a 2 by 2, and my unit square matrix is a 2 by 3. I want you to multiply using matrix multiplication, multiply the transformation matrix by the unit square matrix. Right? So what am I going to do to the unit square? I'm going to transform it. So this is my function. This is the input. What's the output? So let's multiply them. Right? So when I multiply them, I'm going to get a 2 by 3 matrix. And I'm going to follow the rules of multiplication. 1 times 1 is 1, and 0 times 1 is 0. Right? Then I'm going to do 0 times 0, which gets me 0. Right? So I'm working here. And then I'm going to do 1 and 0, which is 1. And then I'm going to go to the second row and do 0 plus 0, 0 plus 1, and 0 plus 1. And maybe you are not shocked to see that using this transformation, because it was what? This was the identity for 2 by 2, right? And you can see that this 2 by 3 matrix remained unchanged. Maybe that's not a shock to you, right? So taking this 2 by 3 matrix and transforming it by the identity matrix did not change it. I ended up with the exact same. So that's not very exciting, is it? Sorry. Not very exciting. So let's do another one. So I'm going to do a matrix transformation. This time, this matrix looks almost the same, except the diagonal are 2's instead of 1's. What's going to happen to my unit square when I perform matrix multiplication? Right? Perform that matrix multiplication. All right, when you did you get this? What happens if I now draw that? Remember, this was the, right? These were position vectors, right? This was position vector 1, position vector 2, position vector 3. What happens when I would draw that? I would go to 2, 0, 0, 2, and 2, 2, and connect those. And what do I get? Hey, that's still a square, right? Right? Here's the unit vector, and when I connect it, I still get a square, but what has happened to my unit square? It got bigger, right? And as a matter of fact, it got bigger by a factor of 2. So we can say that this transformation You perform the matrix multiplication, and you figured out that result of this transformation was it scaled the unit vector, the unit square, by a factor of what? So can we predict, what would happen if instead I made this matrix 1/2 on the main diagonals? What would happen then? You would get a smaller, right, square of unit vectors 1/2, 0, 1/2, 1/2, and 0, 1/2. Right? And if I connect them, I get another square. Crazy. What about 3? Can you imagine doing 3's, right? So a transformation matrix of this form seems to have some kind of scaling impact on the entire square. So let's try out these transformations, and maybe you can pause the video for a second and see what these transformations, perform. Again, take the second transformation, multiply it, right? So take this one up here. We're going to say 2, 0, 0, 1, and you're going to take this as your function. You're going to multiply by the unit square, the matrix made up of the position matrices for the unit square. Then tell me what the result is. So what's the result of this matrix? Right, so step 1, what is the transformation matrix? Step 2, multiply by the unit square. Step 3, give me the resulting matrix. And step 4, name it or describe what that transformation was. So again, maybe you want to pause the video and do this yourself. But I'm going to go ahead and show you my results. So those are the resultant matrices that I got doing step 1, 2, 3, and 4. So this is step 3 right here for each one of those matrices. And now all I have to do is describe what happened. So if I were to draw on here the position vector that was 1, 0, it got transformed to 2, 0. The position 0, 1, the position vector 0, 1 didn't get transformed at all. And the position vector 1, 1 got transformed to 2, 1. And I connect those. What do I get? I don't get a square anymore. What do I get? Well, I get a rectangle, don't I? So what is the result of this transformation? And again, look at the diagonal. This wasn't a scale factor, it was a stretch, wasn't it? We're going to say that this was a horizontal stretch by a factor of 2. What was this one? not a horizontal stretch, but a and notice the pattern. The pattern was I still had zeros on the minor diagonal, but this time I had a horizontal stretch when the x, right, the unit vector, the x component of the first unit vector was changed, but not the second. Here I had a vertical stretch when the y component of the unit vector in the y direction got changed. So notice that each one of these has the diagonal pattern. Some people call these diagonal transformations, where you've got zeros on the minor diagonal and the only changes occur in the main diagonal. And again, all I'm doing is drawing. I'm doing the matrix multiplication, and then I'm drawing where did 1, 0 go, where did 0, 1 go, and where did 1, 1 go. I did that with each of these. Notice again that the origin always stayed, right? The origin did not, and all lines were preserved as lines. So what happened with this transformation? This was a reflect, wasn't it? So the horizontal vector 1, 0 was transformed by the function negative 1, 0, and it caused a reflection over the y-axis. So maybe you can predict what happens now. Here's the origin, right? And this was just, these were still 1s. This was a negative 1, and this was negative 1, 1. What happened to my vertices with this transformation? This was the resultant matrix, right? 1, 0 stayed at 1, 0, but I then was transformed 0, 1 went to 0, negative 1, and 1, 1 went to 1, negative 1. So I still had a square that was not scaled or stretched, it was just reflected. But this one was reflected over the x-axis. So what happened here? Both of them were changed. You could kind of sort of think of this as a composition of two transformations. What happened? Here's the origin, right? What happened to the new x vector is negative 1, 0. The new y vector is 0, negative 1. Whoops, sorry, it's over here. 0, negative 1. And then I have negative 1, negative 1. So connecting all of those tips with the origin, I get a square that has been (180 degrees. Cool, huh? So we've seen matrix transformations now. What has to happen to our matrix transformation? Remember, you can think of, we started with the identity matrix that did nothing, right? It had no effect. Then we started manipulating, well, what happens when you change the diagonals to the same number? I got a scale. What happened when on the main diagonal I only changed one of the values, right? And I think you could figure out what happens, right? I got a stretch either in the horizontal or the vertical. And then I have a reflection over axes. And yes, these can get more complicated, but this is all that you are responsible for so far. So what if I did something like this then? What if I kind of talked about a combo. What if I said, here's another transformation. What if I said, I had another transformation, but this transformation matrix looked like this. I could write this in function notation. My transformation matrix is times my unit square. Right? So perform the right here's, I guess I should put that in there. What do you think happens? Can you predict what happens without actually doing the multiplication? Right? What's going to happen here? What transformation is that? Right? Isn't that going to flip over x, and what is this going to do? That's going to be a stretch because it doesn't match, right? But what kind of stretch is it going to be? Whoops. It's going to be stretched by a factor of 2. But which kind? Good. So without doing this multiplication, didn't mean to do that. Darn it. Without doing the multiplication, can you tell me what the transformation, I'm not happy with that function notation anyway. With this transformation, what is it going to do without actually proving it with the multiplication? Right? It's going to flip things. It's going to multiply the 0, 1 by 2. And then since it's flipped, isn't this going to be right? Isn't that what I'm going to get? And let's draw these. So -1, 0. Sorry. -1, 0. 0, 2. Oh, this is so terrible. I can't draw straight lines. And -1, 2. Connect the tips. And I do have, right, my unit square has been flipped over the y-axis. Did I say x before? Flipped over the y-axis and vertically stretched by 2. Cool? Now, I want to start looking at some patterns here for a sec. Look back up here at my original. Remember, I was taking this first example, was taking this transformation matrix and multiplying it, right? This transformation matrix, multiplying it times this transformation matrix and generating this one. And then when I sketched this, look what I did, right? Look, this is what I got. But look at what I've highlighted in red here. This was the initial unit vector 1, 0, right? 1, 0 ended up becoming 2, 0. Yes? But that's the same as the column of my transformation matrix, the first column. And then look at my original unit vector in the y direction was 0, 1. And it ended up becoming 0, 2. But look at the column of my transformation matrix. And now, hold the phone, I've got 1, 1. That's the third column. I don't have a third column in my transformation matrix. But look at what I ended up. The column 1, 1 ended up to be 2, 2. Can you look at a 2 plus 0 is 2. 0 plus 2 is 2, and that ended up being my third column. What? Does that pattern hold? Look at what's happening down here. Does that pattern hold with this second transformation? Column 1 became 2, 0, column 2 became 0, 1, and column 3 became 2 plus 0 and 0 plus 1. Oh my Lanta. Column 1, column 2, column 3. Holy smokes. That means I don't actually have to multiply if I recognize this pattern. I don't actually have to do the matrix multiplication. Let's be real, matrix multiplication is a little tedious and annoying, even though I'm dealing with ones and zeros, which is super nice. Wow. Oh, what is this transformation now? My main diagonal stayed the same, but my minor diagonal changed. Well, let's see what's going on. Every time I have a new, I just thought I was all excited because I had a pattern. I don't have a pattern anymore, but, you know, or I'm not sure, so let me just see what's happening to my basic unit, right? I'm going to take my transformation matrix. I am going to multiply using matrix multiplication times my unit square. My matrix, right, made up of position matrices of the unit square. This is what I got when I did that multiplication. Now let me go ahead and graph this, right? Notice that, now let's see if the pattern that we had before, does it still hold? Right? 1, 0 after I performed my multiplication still stayed 1, 0. 0, 1 still stayed, I'm sorry, 0, 1 became what? Didn't stay the same, it became 1, 1. Oh, snap. What was 1, 1 became 2, 1. Well, how do we say we got maybe the third column? Does my pattern still hold? Yay! Now what does the graph of this thing look like, right? The unit vector 1, 0 remained constant. It didn't change. I already had the point 1, 1, but that's not what 0, 1 got, right? Wasn't my old 1, 1. The tip of 0, 1 got shifted over here, right? What was 0, 1, the tip got picked up and moved here. So now I don't have this unit vector anymore. I've got this one. And then the point that was 1, 1 also got moved over to 2, 1. So what does that look like when I connect it? Whoa, that's not a square anymore. What is that? Parallelogram, right? Crazy. We call this kind of transformation a shear, right? Where it's just the top has been taken in this case and sheared over to the right. So we call this was a horizontal shear. By factor of, that's right, 1. So as you can see, I've got a whole bunch more for you to do down here and try where each one of these instances, right, before we only had what we call diagonal transformations, which meant that there was zeros on the minor diagonal. Notice this time that I have, in this case, I've left the main diagonal alone and only changed here, right? Whoops, sorry, pen was dragging there. But here, I've changed the main diagonal, so you have to remember from previously what that does, but then I've also done I've got a shear factor. I've done something along the main diagonal, but I have a shear factor. I've done something along the main diagonal, shear. And then here, I've left the main diagonal alone and changed both of these by the same amount. Now, I could have you multiply all these out, but if you run this, there is a hyperlink behind here to a nice applet. So maybe write these down or take a picture of, listen, see what I did there? I took a picture, and I'm going to go to this applet. Oh, this is not the one I wanted. Rats. This is nice, but it wasn't the one I was after. Sorry. All right. I don't remember where I linked that to. Ah, there it is. Okay. Okay, so what I like about this one is that you can type in here your transformation matrix. So, for instance, here is my, right, here is my unit square. And then some of the things that we have done so far. Look what happens when I want to reflect across the x-axis, right? My transformation matrix automatically got changed. Also, look what it, right? And there's, so this is where I grabbed those pictures from. What if I wanted to reflect across the y-axis? What if I wanted to scale by a factor of 2? What if I wanted to stretch by a factor of 2? And again, look at my matrix transformation up here, right? This should look familiar. Vertically stretch by a factor of 2. Shear by a factor of 1. That's where I got that picture. Look here, I'm going to shear by a vertical factor of 2. Can you predict what the transformation matrix looks like? Right, look at that. Can you see what the transformation looks like? Right, the 1s stay the same. And since it was vertical, I'm putting it down here, which should make sense. So now let's do the ones that I, instead of actually doing the multiplication, what happens, I think we already saw the first one, right? I made this a 1. And what was that? That first one was a, can you see what it, this has been a shear, right? But it's not been a shear, and it's not a horizontal shear. It's been, right? These points have been moved up here. The next one I asked you to do was the transformation matrix 2, 1, 0, 2. So that is, right, a dilation, a scale factor of 2, and a horizontal shear. Right, do you see that? Right, there's where the 0.11 went. Here's where the 0.10 went. Here's where the 0.01 went. So, right, I think this is pretty cool. I like this. And I'll fix the PowerPoint so that the link is in the right, -1 and 0 and 1. What happens here, right? This is a, right? See, and we talk about the tips moving, but you know, every point moves, yeah? Right? So hopefully you can see that what we have here is shears, right? So we've got horizontal shears, vertical shears, dilations, stretches. So those are the matrix transformations that you are responsible for. Scale, stretch, reflect. Shears and combinations of those. And remember, our pattern still holds. We don't actually have to multiply. So, a summary of sorts. The image of the unit square has been transformed by the matrix ABCD. Right? Remember we talked about this. If this is my transformation matrix, on the unit square, the resultant matrix has the same first column as the first column of the transformation matrix. The resultant matrix has the same second column as the second column of the transformation matrix. And then the third column of the resultant matrix has the sum of the first row and the sum of the second row in the third column. And this is what the matrix multiplication would look like. Right? And if you do that multiplication, you can see that this is what you get. Right? So remember, my result is an image of the unit square, which was made up of position vectors. under a given transformation. Now what I want you to do is I want you to find the determinant of all our transformation matrices. Remember, our transformation matrices were all 2 by 2. So when we know the determinant, we know how to find the determinant of all of them. So I'm just going to rewrite them here. These were all of the transformation matrices that we did, right, on that first slide. So what's the determinant of this first one? Well, this seems like an exercise in, I don't know why. Whoops, I'm sorry. Oh yeah, this is. Crazy, right? Now I'm going to go back a couple of slides and I want you to think about these numbers. And I'm going to go back a couple of slides. Oh, rats. Here. No, here. Remember the unit square when we performed the first transformation, which was 1, 0, 0, 1, and we drew that square and we got an area of 1, right? The unit square has an area of 1. But then we did our first transformation, which we now have figured out was a scaled up by a factor of 2. And what is the area of this now? Right? The area of the transformation 0, the area under the transformation of our first transformation, what's the area in the resultant square? What was this determinant again? What is the area of this rectangle? Wait. What is this determinant? What is the area of this rectangle? Oh my Lanta. What's the area of this rectangle? Sorry, this one's a square, isn't it? And what's the, oh. Gee. Area should always be what? Oh, huh. Well, isn't that something? Isn't that something? The determinant of a 2 by 2 matrix is equal to the area of the representative square or rectangle. What? Hey, does that work for our parallelograms? What's the area of a parallelogram? Isn't the area of a parallelogram still base times height? And what is the base of this one? And what is the height of this? So what's the area? Whoops, sorry. Yeah, the height is, right, the height is perpendicular. And what is the determinant of this matrix? Oh my Lanta. Now, I purposely didn't do this one when we were on that applet, and I didn't do that on purpose. But can you tell me what that determinant is? This is 1 minus 1, which is 0. Well, that's weird. Using our pattern, what would this be? Right? The resultant matrix would be 1, 1, 1, 1, and then 2, 2. What would that graph look like? Remember, 0, 0 is always there. So the unit vector 1, 0 got transformed to 1, 1. The unit vector 0, 1 also got transformed to 1, 1. And the unit vector 1, 1 got transformed to 2, 2. Hey, where's my square? Where's my rectangle? Where's my parallelogram? You ain't got none. So, what is this? What is the area of this resultant thing? It is 0, right? I just have one dimension. This transformation is called a projection, which will become important again in higher level math classes, but you are not responsible for projections. But I do want to just go back to the back here, and I want to go ahead and put in 1, 1, 1, 1, and look at what you get. Notice down here what happens if I ask for the projection. A projection. Now it just didn't do as long of a one, but I could make it oops. Well, I don't know. I need to go the other way. Anyway. Right, I can scale this up as I want. Crazy, right? So, finding the determinant of all our transformation matrices yielded this result. The absolute value of a determinant of a 2 by 2 matrix is the area of the image of the unit square that has undergone the transformation A, B, C, D, right? And the determinant is of this 2 by 2 matrix is the product of AD minus the product of BC, and you need to take the absolute value because area needs to always be positive regardless of where you've put, put the, where on the axes you've placed the figure. Whoa. Well, we've done a lot of work in 2 dimensions. This is easily, right, this same thought process holds when we go to 3D. The image of the unit cube that has been transformed by this matrix, A, B, C, D, E, F, G, H, I, and remember the unit cube is from the warm-up, right, 4 matrices where I'm dealing with the unit vector 1, 0, 0, the unit vector 0, 1, 0, the unit vector 0, 0, 1, and then to make it a cube, 1, 1, 1. Right? That's my unit vector. If I take this, which is a what, 3 by 4, if I take a 3 by 4 unit vector and I use left multiply by the transformation matrix, do that multiplication, and this is what you're going to end up with. And our same pattern for the last column holds. So your transformation columns tell you where each of your unit vectors have gone, and then your last column is a sum of the rows, which are the operators out there on the 1, 1, 1 point. And yes, the absolute value of the determinant of that 3 by 3 matrix is indeed the volume of the image of the unit cube that's undergone this transformation. Whoa!